Okay, I'm going to go to OS Dev to see what kind of trouble I can get in. Let's see what they probably misunderstood something. So let's see what we have here. Hold on. Okay, what's new? We'll start with IDT problems. And now, when I initialize my IDT, I don't use stubs or you can see this guy has some IDT set entry. Okay. You see how he has stubs? What I do is so the first 20 are false, or the first 20 hex, first 32. What I do to initialize is to for the first 20 I do it like that. For the rest of them, I compile a wait. Each do you see here? Right here it is compiling code. So the reason I don't have stubs is because this is the machine code for a push. Then I push the number of the interrupt or the vector, and this is a jump, and then I push a relative offset. It's the address of int fault minus destination. Destination is the it's a relative branch, so that's the current location. So this is how this compiles, basically, more or less. So that's what I do for the fault. What do I do for the rest of them? The first 20 are false, and the others I initialize the others to no op. No op acknowledges all interrupts and returns. So that's anyway. So that wasn't very interesting. Debugging OS on real hardware. You have to make a debugger. So in my operating system, in my compiler, I wrote an unassembler. In the way I have a file that has all the opcodes and addressing modes. I had to type this in by hand. And what it does is to unassemble it does a binary search in a the tricky part is the the machine code instructions are variable length. So what you have to do is you have to make a way of sorting the machine code instructions, and then once you have a sorted list, then you can do a binary search. So in my unassemble, I came up with a way of comparing two instructions. Once you have a way to compare, then you can do a sort and make a table. And then once you have a table, you can do a binary search. So that's how that works. I have symbolic debugging because I have symbol tables, and my compiler is designed to make symbol tables that my debugger can use. You can say debug. This brings you to my debugger. The best thing it has is a stack trace. You see how it gave a stack trace? You have to be sure to use RBP for your stack frame, and then it can do a stack trace. Anyway, so I have a native debugger, but I mostly do printf debugging. If you're making an operating system, you start with, well, you don't have an assembler at first. The first thing you make when you're starting on native hardware, you make a dump instruction. That's the first thing you make. Once you have that, the next thing you make is dump registers. Then once you have that, you start making your serial communication console routines and stuff. Anyway, I think I have dump address. This is for the stack. So it tells what the addresses correspond to. Anyway, that's off the stack. I have caller report. That gives a stack trace. So dumping an address dumps the hex and looks up the symbols. Dumping or caller report climbs the stack. You can see the this is going by 8. This goes by, you know, a couple hundred and stuff, depending on how much room on the stack each function takes. Anyway. Okay, this is a nightmare. I don't even do any of this. Where are we here? Okay, someone wanted to know if I was going to do other keyboards. That's really a nightmare because there's there's 100 international keyboards. I don't know. I'm just saying it's a lot, and I don't want to do that. I don't want that crap in my operating system. So what somebody from each country needs to why don't you make a version for your country, and I'll post a link on my webpage. I don't want to do that. I don't want my version. What I want is, the whole purpose is for it to be simple, like a Commodore 64 was. So your country should have the simple version for your country. Once it starts getting ugly and messy, then that's not how it's supposed to be. It's supposed to be like a Commodore 64 was. So I don't want to do international. I'll do 2 fonts. There's an acrylic font that I heard about. This has Russian symbols in the upper 128. What I want is, I'll have it switch between 2 fonts. Standard and okay, I don't see anything here. Anyway, now my operating system is not symmetric multitasking, symmetric multi-core. On mine, each application has to explicitly create slave processes on the other cores, slave tasks. So on mine, if you make a flight simulator, it's using 8 cores, and each core is assigned a different strip. So it's not multi-core. Other operating systems move the tasks around from core to core. We don't do any of that nonsense. You just explicitly create a task on each core, and what you need to know for multi-core is you need to know MP count is the multi-core count. You need to know spawn. Spawn works both for regular tasks and multi-core tasks. You specify the CPU. -1 is the current CPU. So you need spawn, you need MP count. And then the other thing you need is a CPU record. The CPU record has the core number. GS points to the CPU record. The only thing you need from there is the core number. So let's do a little multi-core application. MP whatever demo. Okay, it takes one. Let's make this MP count. That's multiprocessor count. Spawn. MP demo. And then here, this is basically standard standard out. I'm passing standard out as, okay, let's look at the arguments. You pass the address of the function, you pass a data that gets passed to the function, you pass a name and a core. Okay, so this is the name, and then we give the core. And inside here we say doc print doc %d. And then gs num is the core. So what do you think this is going to do? Okay, so it printed out all the cores. Now, let's just do a little example. So we're going to have 8 cores, increment a global variable. Okay, so what do you think is going to go wrong? Okay, so what did we get? We got 2 million. It should be 8 million. Any idea what the problem is? Well, the problem is when you're doing multi-core, you have to lock, if you're accessing the same location, you have to lock the cache line. So this puts, shit, maybe we didn't wait long enough. Okay, hold on, let's back up. Okay, we got 12 million. Let's wait a little bit longer. Okay, we got 16 million. Longer? We almost got 20 million. Longer? We got 19 million. I'm counting to 1 million. Oh, we still have those tasks going. No, we don't. What the hell's going on? Oh, we didn't. I'm an idiot. That's not very funny. Okay. Okay, 3 million. Let's try again. 3 million. Let's kick it up. Okay, 3 million. So we get 3 million. We want 8 million. Let's try it again. 3 million. We want 8 million. So if we put a lock on here, you can count to 1 billion without much problem. I was pretty stupid. So look at that. Exactly 8 million. Isn't that beautiful? So that's from, we should unassemble it. It's using a machine code lock prefix. So if we unassemble function, MP, so it's using a machine code lock prefix on. So, what I do, I like to do this exactly the same. MP, what do I call it? Okay. Okay. So let's. So the. As a matter of fact, you don't want to. I have a couple warnings. When you're doing MP code, I have a couple warnings. One warning is don't exit while the MP tasks are running, because when you exit your task, the memory gets freed. The memory for this function has to be kept safe so long as the MP cores are running. So you don't want to yank that memory out from underneath them. So that's one warning. I'm going to show the standard way for doing MPs. So you have flags for as long as it's not done. You set, let's look at this. If we have 8 cores, it takes 1 to the 8th, which is 256, minus 1, 255. So that's equal to 0, that's equal to binary. That's like 8 1. I don't know. I just want to show that it's got 8 ones. And locked bit test and reset. This has a lock prefix. It's the same sort of lock as that, and it's a bit test and reset. If you're wondering where I came up with bit test and reset, if you go to the Intel datasheets architecture manual 2A. This has the assembly code, the machine code, the assembly code instructions. And if you'll notice, bit test and reset is a x86 instruction. Bit test and reset, bit test and set, bit test and complement, bit test. And TempleOS is only for x86. I don't think twice about making unportable. I don't worry about portability. I worry about x86 alone. So this, well, anyway. Oh, so at one time I made an option for less than all the cores. So that particular, never mind. Okay, so you see it's pretty damn fast. So just for your information, if you're doing something with a lock on it, I think it's not faster with multi-core, because if it's you can only do one thing at a time, and if it's got a lock, I have a feeling it takes equal time to do it with 1 core or 8 cores. So you got to be doing other stuff other than locked things. Do you understand what I'm saying? I think if you measured the time for 8 million locked, you want to do that? We could. We got nothing better to do. F64 T0. I like to do it this way. I guess we should. T0 equals T sub S. Something like that. T sub S minus 0. So it takes 15/100 of a second. So let's do the same thing with I think this takes us exactly the same time, more or less. Well, it's even worse. That's not too surprising. Now, if you don't have a lock, it's probably nanoseconds. Okay, I'm surprised it's not even worse. Anyway, so this is not a good argument for multi-core. Anyway, let's see if anybody's here. Is there anybody listening? Hello? Let's see if anybody's here. Is there anybody listening? I'm not really a communist. Socialist. Those crazy socialist hippies. So what else is there to talk about? So how can we tell how many people are here? Is it not very many? Oh well. So you want to do a miracle? Let's do a miracle. Okay, Mr. God, say hello. God says. Okay, well, I don't really have much to talk about. Let's see. Let's go to Drudge. God, why are you flooding Texas? Is Texas evil? I'm just kidding. Trawlers. Day film. I was on the air for 9 hours. Something silly. So you want me to work on the circuit simulator? Egads. I haven't touched that in a while. So you can find it. Okay, so you can find it on my website. I can show you where, but it's not any use. So we're going to place a resistor, replace a capacitor, place a capacitor, resistor. Let's do it. Inductor. And then you can connect the components. And it tries to figure out the lines. Let's put a resistor. That doesn't look good. Okay, so now you move them around. And how come? What happened? That's pretty messed up. Well, not having much luck. I couldn't even get my circuit layout, let alone do any analysis. This is hard. You think it's easy? It's not easy. Oh well. CPZ. If a file ends in Z, it's compressed, and otherwise it's a, I call them C++. It's actually wholly C, but I didn't want to, how do I put this? If you make it foreign, people don't like it. Technically, I should have my own text file. I should say doldoc or dd. I should do something like dd, but I don't really want to. I don't want to be that strange. So even though it's not a text file, I say it's text. Even though it's not C++, it's like C++, but it's not. So I do it. You know, maybe you can call me bad names for not making my own. But it's kind of like I call it a kernel. At first, I used to call. I have a kernel directory, even though it's not really a kernel. It's not, the whole thing is ring 0, so there's really no kernel. It doesn't really fit. I mean, it does, but basically, you know, if I were really famous, I would worry less about what what people think. So if I had a guarantee of being famous, then I would go ahead and change these to HC for Holy See. But I don't want to do that at this stage. Those should be HC files, Holy See, and the text files should be DALDOC or something like DD or something, HC and DD. But I would really that would be a bad political move. At this stage, I can't afford to be. That's from a popularity standpoint. I would lose too many people. That's from a popularity standpoint. I would lose. So. Okay, well, that's enough.